Mr. Tarun, that was nice. All right, so introduction to two-dimensional vectors. Yeah, yesterday was a train wreck. We're going to try this again. The mathematics of this section, there's a lot of formulas in here. There's some new language, new letters. But at its core, there is really hardly anything new that you have to do in this section. All of the math is based on what you learned in Chapter 4. So I'm going to start with a little bit of trig and then expand into some notation of vectors and kind of build off of that. So we're going to take the question, which is we have an angle in standard position, so a little bit of fallback from Chapter 4, like I said. And we've got an angle in standard position whose terminal side passes through the coordinate of 4, 3. And I would like to know, what's trig a study of? Oh my God, that was beautiful. Angles and right triangles. So we're going to find theta, and we're going to work with the reference triangle. Yes, this sounds just like yesterday, only we're not going to flub this up today. We're going to work with this reference triangle that has a side of 4, a side of 3, and I'm going to ask you, what is R? What is the length of the hypotenuse? Or if we were talking about, wouldn't be a unit circle, but if we were kind of expanding on the idea of a unit circle, what would be the radius of that circle? Who can help me out? Tell me how to find it.
4 squared plus 3 squared.
Yeah. R is equal to, or R squared is equal to the x squared plus y squared, or R is equal to the square root of x squared plus y squared, or R is equal to the square root of 4 squared plus 3 squared, which is going to be the square root of 25, or in other words, R is equal to 5. Now, Jason just told me the answer was 5 because I'm obviously trying to pick a question and design a question that we can do easily in class. That R is equal to 5. And we should know that because it's a 3, 4, 5 triangle. It's a Pythagorean triple. Okay? So what if I wanted for this right triangle that we know all 3 sides of now, x is 4, y is 3, and R is 5 for this reference triangle, what is the angle, what is the measure of this standard position angle? How are we going to figure that out?
Use the law of cosines.
You want to do law of cosine for a right triangle.
Sorry.
Just, I mean, it'll work, but you can inverse any trig function because we know all 3 sides. I'm going to go with the standard one. You said inverse sine. We know the opposite leg and the hypotenuse, so that will work. We also know now the adjacent leg and the hypotenuse, so that will work. And so arguably when you know all 3 parts of your reference triangle, you can find the measurement of the 2 acute angles using any trig function you want. Textbooks will always default to working with the tangent function, but that's simply because, you know, like back in Chapter 4, we were given a point that the terminal side passed through. We were given x and y. So our standard formula for finding this angle would be the tangent of theta is equal to y over x, or the tangent of theta in this case is going to be 3/4. And how do we get theta out of the tangent function? We apply what to both sides? Arctan or inverse tangent. So then theta is going to be arc tangent of 3/4. Of course, I don't care if you do, you know, inverse tangent notation either. Theta is going to come out to be 36.9 degrees. Okay, so that's all language of trig. And that is all we are doing with our two-dimensional. And if you extend this area of mathematics, you'll quickly move into three-dimensional vectors. And those of you that are in physics are going to probably be able to help me a lot over the next few sections of this book, because this is where the world of physics and trig come together quite a lot. But if I now focus on some vector notation, let's call this hypotenuse of this right triangle. Let's call this vector v. Now, vector v, which I'm highlighting in green, but that's not going to show up if I write a bunch of green, so I'm going to write it in black. Vector v in component form, there's three ways to write this in component form. When you're writing vectors in component form, there is a times vector I plus b times vector j, and I'll describe what the hardest part about teaching vectors to begin with, which is what I was trying to do yesterday, is like there's just so much vocab that I have to throw at you and explain, but ultimately it's just the same math that you did in chapter 4 initially. So I'll explain this in a minute, but there's a times vector I plus b times vector j, and I hate this notation, but textbook use it a lot, and it has its place, but I just don't appreciate it. We can also write this vector notation in component form with some pointy brackets. Now in pointy brackets, we can write vector v in the form of again, I don't know what to call this, but a pointy bracket with a comma b. And your textbook is going to have this notation quite a bit in it. It's sort of a shorthand version of a times vector I plus b times vector j. The problem with this notation is too many of us just write these pointy brackets as parentheses, and then your vector looks like a coordinate notation, which is no good. Now, it's not like IB made this up, but there's another way of writing component form of vectors, which honestly I did not see until teaching IB, and now I absolutely just love it, where it's a set of tall parentheses with a stack of letters. Now, we also are going to use this sort of notation, and it's going to be confusing when we get into probabilities and we start talking about permutations and combinations. So this symbol here, this notation, will have its issues with another area of mathematics, but it's not as monotonous to write as a times vector I plus b times vector j, and it also is not going to be, if your handwriting's sloppy, start looking like coordinate notation. So I much prefer this component form of a vector. Now, when you start talking about vectors, vectors are defined by magnitude. This magnitude might be wind speed. This magnitude might be amount of force applied in a certain direction. If you're talking about in the world of physics, but it's the length of the vector. So vectors are defined by magnitude and direction. And the magnitude is going to be found by saying that we have an absolute value. Now, there's all kinds of stuff back here I still need to talk about, okay? But let me go on this tangent for a minute. So, the magnitude of a vector, when you see a vector symbol, which is going to be a letter with like a directed arrow over it, I'm not also, and there's another sort of definition of a vector I need to give you. But the magnitude of a vector is the length of the vector. And you find the magnitude of a vector the exact same way you find the hypotenuse of our reference triangles. It is the square root. Now let me pause here for a second. Again, there's so much stuff I want to say at the same time. I can't get it out fast enough. Vectors are defined by their magnitude and direction. So I'm about to write some different letters in this square root function. It'll be similar but not exactly to this notation. I'm not going to write the square root of x squared plus y squared. I'm going to write the square root of a squared plus b squared. So when you see the letter a in vector world, that is equivalent almost, I'd say it's going to be similar to the variable of x in sort of like basic, standard position trig world. When you see the letter b, that's vertical movement, similar to the variable of y. Now the difference is, let me talk about direction. And then direction is going to be tangent of theta as that sort of standard textbook formula, that's given to you to work with, though, as we know from trig, if we know all three sides of a reference triangle, we can use any trig function we want, but the standard textbook given formula is the tangent of theta. Now, I'm not going to write y over x. I'm going to write b over a. But these formulas are effectively the exact same formulas you had in trig. Vectors are not defined by their position. They're defined by their direction and magnitude. So, stating that in our example, vector v has a magnitude of 5 and a direction of theta equal to 36.9 degrees is a standard way of talking about magnitudes. Okay. This is like plain language of vectors. So any vector that I draw that has an angle, so maybe I start over here at not 0, 0, but, and this is what I was trying to do the other day, like if I want to start my vector at 1, negative 4, if I draw a vector that has an angle that is equal to 36.5 degrees and has a length of 5, then I am drawing vector v. When you draw a vector, its initial point, the first point that you put down does not have to be at the origin. It can be at any point in space. Thank you, Mia. 36.9 degrees. Now, that's all great and dandy, but saying that a vector has a certain length and a certain direction will not be friendly for combining forces, okay? If you have multiple vectors that you want to add together, like a plane going in a certain direction with amount of force coming out of its engines, and then like a crosswind pushing that plane in one direction. If you have multiple forces in some kind of space working together, you're going to want to be able to do some arithmetic, some mathematics, some operations of vectors. And vectors described as a length and a direction are very, very unfriendly to do math on. So if I want to write a vector v in component form, so I'm going to kind of take this one setting and beat it, just use it constantly all periods so I can like talk a lot of vocab without doing a lot of math. So if I want to write vector v that has a magnitude of 5 and a direction of 36.9 degrees, write vector v in component form. I'm going to give you a hint. We already have the answers. But if I have vector v that is starting at some random point in space, but going 5 units in a direction of 36.9 degrees, the components of that vector are the horizontal and vertical components. That horizontal length is going to be described by the letter A. And that vertical component is going to be described by the letter B. So again, falling back on chapter 4, if we have a right triangle and the components of every vector are always perpendicular, there is always, no matter what vector we talk about over the next few days or weeks, there's always going to be a horizontal and a vertical component to every vector, regardless if it kind of points up in quadrant 1, quadrant 2, quadrant 3, or quadrant 4. At least we'd be saying quadrants if the initial point was the origin. So given the hypotenuse of 5 and the angle of 36.9, how do we find A? From theta, what's A? The adjacent leg or opposite leg? The adjacent. So we have the cosine of theta is equal to A over not C, not R, but the magnitude of vector V. Anytime you see straight lines around vector notation, that means length. And the vector that you're working with is always going to be that hypotenuse, unless it's, of course, a horizontal or vertical vector. But unless your vector is horizontal or vertical, the hypotenuse will be your vector, and the horizontal and vertical legs will be the components. So if you want to find A, you're going to be doing the cosine of theta is equal to A over the magnitude of vector V. In chapter 4, we would have called that just simply the length of the hypotenuse, or R for radius. So the cosine of theta, the cosine of 36.9 is equal to A divided by 5. So A is going to be basically approximately equal to what? I'm just doing the same example backwards. A is going to be equal to 4. This is a formula that's presented to you in this introductory section of vectors as a new formula. The only thing new about it is the hypotenuse is written as the magnitude of vector V. 2 chapters ago, we just called that C or R. And if you want to find the length of B, the vertical leg, the vertical component vector, from the 36.9 degrees, what leg is this? Opposite over 5, which is the hypotenuse or the magnitude of vector V. So another new formula, if you even want to call it new, is that the sine of theta is B over the magnitude, again, of vector V. Again, presented to you in this section as a new formula of how to work with vectors, but it is still just basic right triangle trig from chapter 4. Just with R or C that we know of from Pythagorean theorem being replaced with magnitude of the vector. And so the sine of 36.9 is equal to B over 5, or B, which is 5 times the sine of 36.9, is going to be approximately what? Now, so you now have formulas that will convert a vector given in magnitude and direction into component form. These are like new formulas. We are going to be doing word problems. We're doing the basics today, the fundamentals of vocabulary, the basics of vectors. But we're going to be having questions, being given questions that have tugboats pulling with a certain amount of force at a certain direction, working together to pull a barge somewhere, or a plane with so many pounds, probably won't be pounds of force, but a plane going a certain direction or a certain speed at a certain direction with a crosswind, with a certain speed in a certain direction, and find the resultant vector of where that plane's really going. Lots and lots of examples where we need to add vectors. We need our vectors in component form to work with them. So we already know this, but vector V in component form is horizontal component over vertical component. Or back here we have this vector, vector V, we knew already because the original problem was 4i plus 3 times vector j, or 4 over 3. That's a lot of math, and I haven't really technically defined what a vector is. This black thing here, this hypotenuse with a point and an arrow, looks like a what? A ray. It looks like a ray. But rays go on forever. Vectors have a defined length. So a vector is a directed line segment. They're a line segment, not a ray. They do not go on forever. When you look at a vector, or there is an initial point, so this is the initial point. There is a point that the arrow stops at. That is your terminal point. There is the vector itself. So let's one more time call this vector v. There is a horizontal component, A. There is a vertical component, B. The components are always meeting at a right angle, but there is also some kind of theta. Anyway, when we say that vector v is A times vector I plus B times vector j, I is a unit vector. Oh, another vocabulary word you haven't heard me say yet, only I'm putting it in the definition. Vector I is a unit vector in the horizontal direction, which is not worded very well. So let's try again with vector j. Vector j is a vertical. Probably should have used the same colors as over there, but is a vertical unit vector. Okay, well, that's great, Mr. True, but what the heck is a unit vector? Any idea what a unit vector is?
It's like a vector that's one unit in a specific direction.
There you go. All a unit vector is any vector with a length of 1. What's a unit circle? A circle with a radius of 1. So the definition of a unit vector has nothing to do with direction. A unit vector is simply a vector with a length of 1. So a unit vector is any vector has a magnitude equal to 1. So once again, for yet another example, I've lost count what I've done. So for another example, write a unit vector in the direction of vector v, which is, I know this will be shocking, vector 4, 3. Whoa. Calm down. We can do this. Okay. So if vector v has component form of 4, 3, then how am I going to draw this vector? You're doing this thing, but I don't know what that is.
Yeah, well, you would draw a triangle.
Yeah, I'm going to pick a point. I can pick any random point in space. I do not need to draw this vector starting at the origin. I don't even really have to draw an xy axis. So I'm just going to do a little cross, but that could be 0, 0 or 27, 13. I don't know where the initial point is. But from this initial point, I'm going to go over 4 units and up 3 units to draw my vector v. These are the component vectors, or the components of vector v, which is right there. That is vector v. Now, if I want to change the length of this vector to have a unit or length of 1, the first thing I have to do is find out how long this vector is. I'm sure no one knows what this answer is right now. So how do we find the magnitude of vector v, or the length of 5? Okay. So this vector has now a magnitude that's equal to 5. We want to make that smaller. I want to take this triangle. There's a formula attached to this, and I bet you don't need it because you understand similar figures from geometry. I'm going to be optimistic and say you do. I'm also going to explode this diagram because I don't like how small I made it. And I want to shrink that triangle down till its hypotenuse is 1. And we need to find a new component form, a new component of A, basically, and a new component of b. Now, when we talked about the sine of 30 is 1/2, did it matter how big the reference triangle was? No. Doesn't matter if it's 1, 2 square root of 3 or 10, 20, 10 square root of 3. As long as the angle is the same, all the ratios are the same. So these two triangles are similar. What does it take for two triangles to be similar, two polygons to be similar from geometry?
Do they need the same angle measures?
They need all the angle measures within the polygons to be the same, yes. Let's talk about the lengths of the sides. The proportion or ratio of change of each corresponding side has to be the same. So if we're going to take the length and divide the length by 5 to get 1, what are you going to have to do to the components? Divide them all by 5. So there is this idea of something called a scalar multiple. Easy math, just new vocabulary. So we need to talk about something called a scalar multiple. If you have a vector v that is described in component form as a, b, and you want to take that vector v and multiply it by some kind of scalar multiple, then that is going to be that scalar multiple multiplied to a, the component form of ab, which is going to be equal to c times a over c times b. And that gets extended to a definition of a unit vector, which is a unit vector is found by taking some vector and multiplying it by, which really looks like division, but multiplying it by 1 over the magnitude of that vector. So if I want you, if I need you, if I ask you to write a unit vector for that goes in the same direction of a given vector, step 1, I'm giving steps. I know you're excited. Step 1 is to find the magnitude of that vector. And then step 2 is to make that magnitude into a scalar multiple. So multiply vector v by 1 over the magnitude of that vector. Or like you did in geometry. If you were told that two triangles were similar, then you knew the ratio of change, the proportion for all the corresponding sides were the same. So the hypotenuse is going to get shrunk from 5 to 1. So all the sides get multiplied by a factor of, well, 1 over 5. So our unit vector is going to be 1/5 times vector v, which I'm just going to write for notes. Hopefully by now it's painfully obvious, is 1/5 times the vector in component form of 4/3. Which is to say your unit vector is going to be 4/5, 3/5. And that's how you create a unit vector. Just find the magnitude and divide out the length. What you did in geometry. But it looks more complicated. You know, the notation looks more complicated because we're in the world of vectors. But there's no new math in this section. It's just a lot of new notation and language because it's vectors instead of just right triangle trig or geometry. Can I beat this question up even more? I can come up with yet another example off the same vector. All right. I know you're excited, but I don't want to do math. I don't want to do like a lot of Pythagorean theorem. Okay, I shouldn't have erased that definition of scalar multiples, but that's okay. What defines vectors? Magnitude and direction. So what makes two vectors equal? Two vectors are equal if they have the same direction and same magnitude. Let's talk about parallel vectors. So two vectors are parallel if they are scalar multiples. This will be another riveting, very difficult question. So calm down. I'll help you through this. Determine if vector u, which is equal to -8, -6, is parallel to vector v, which is 4, 3. Now, I know this is really, really hard. So let's look at the horizontal components. What's, in terms of the horizontal components, what's -8 divided by 4? -2. For the vertical components, what's -6 divided by 3? Also -2. So they are parallel. So therefore, we have shown that -2 times vector v is equal to vector u. Therefore, vector u and vector v are parallel. Now, just to make sure we understand what that looks like, when you draw vectors, what defines a vector? Direction and magnitude, not their location. But for teaching purposes, I'm going to draw these two vectors starting from the same point. So if I pick a point in space, kind of high so I don't have to bend down to draw it, okay? From that point, if I move right 4 and up 3, so 1, 2, 3, 4, and try and keep this the same, 1, 2, 3, there is vector v. And if I keep the spacing the same, let's see if I can manage to do that. This isn't graph paper. If I go to draw vector u, I'm going to go back 8. So 1, 2, 3, 4, 5, 6, 7, 8, and down 6. So 1, 2, 3, 4, 5, 6. So I'm down here somewhere. And if I've drawn this good enough, and I'm going to kind of force it to look right, that's vector u. So vector v has, how have we done already? Vector v has this angle, and vector w has this direction or this angle. What does theta and beta have in common? What do we call this in trig? The same what? They have the same reference angle. So they go in opposite directions. So vectors that go in the same direction or opposite direction will be considered parallel. All right. All the fundamentals, all the vocab is basically done. Tomorrow we're going to do some like application and word problems. All right? Have a good one. Bam! Go do your homework, except you can only do the basic stuff. We didn't do any like application problems. Woo! All right. That was pretty good.